Okay, this screencast we're going to go over the mystery charge problem from your Mastering Physics assignment last night. And the problem talks about a blue sphere at the origin with a positive charge, a red sphere at coordinates d1, 0 with an unknown charge, and then a yellow sphere at a fixed point, which is down lower with an unknown charge, q yellow. And we find the net electric force on the blue sphere. The net electric force on the blue sphere has a magnitude F in the negative y direction. So I'm going to go ahead and show that right now. It's got a net force in the negative y direction. So we have to figure out the sign of the charge on the yellow sphere, and then it's going to ask us the sign of the charge on the red sphere. So the electric force only has two directions, right? Either attraction or repulsion. So the three objects involved here, blue, yellow, red spheres, the blue sphere is being acted on by the yellow sphere and on the red by the red sphere. The only way it can have a net force in the y direction, and I'm going to try to draw this for you here, the only way it can have a net force in the y direction is if it's attracted to the yellow sphere in a line that is along the line to the yellow sphere. Let's say this is the yellow sphere right here. And it's repelled by the red sphere, which would be this way. That's the only way that you're going to have a net. And I actually drew that a little bit too long, so let me get rid of that and draw that an appropriate length, about that long. The only way that you'll have a net force in the negative y direction on the blue sphere is to have an attraction to the y and a repulsion from this. If that's the blue, that's the yellow. You've got a repulsion from the red sphere. Sorry, gosh darn it. Red sphere, yellow sphere. A repelling force on the blue sphere by the red on blue, and attracting by yellow on blue. So those two will come together to form a negative y component. Here's y. Put them tip to tail. There's the one, there's the other. The net force of those, when I put them tip to tail, and then I go from the tail of the first to the tip of the last, I can get a negative y direct force. So if that's the case, and we know that the blue sphere at the origin is positive, then that must mean the red sphere is also positive, because it's the one exerting that repelling force right there. And it must mean that the yellow sphere is negative, because that's attracting this guy right here. Okay, so that's how you figure out the signs. Well, then in part C, it's going to ask about the magnitude of the net force on the blue sphere, assuming, I think the yellow has a magnitude of 2q. Let me check that. Okay, it wants to know what is the charge on the red sphere. So we want to know q red based on the fact that the blue sphere is positive q, and we decided that this is negative, so it's a negative 2q. And then how does that affect the red sphere, the net force on the red sphere? To answer that question, I'm going to actually use the force diagram from the blue sphere, but I'm going to go on the next page to where I've got a little more room to do that. Okay, the blue sphere has a force diagram. It looks like this. Force of red on blue, and then I've got a force down here which is force of yellow on blue. And I know that the net force on the blue sphere is straight down, which is very important, because that means the force of the red sphere on the blue sphere, the x component of the y force, is exactly equal to that. Those two forces cancel out. So the component of the force of the yellow sphere on the blue sphere is exactly equal to the total force of the red sphere on the blue sphere. That's going to help us here in a second. This is yellow on blue y. Okay, so the net force then on the blue sphere is straight down. That's the y component of the yellow on blue. So how does that help us? We're going to quantify, not quantify, but we're actually going to show the, move this up a little bit, express the force of the red sphere on the blue sphere in terms of their charges. Well, I know the blue sphere has charge Q. I don't know the charge on the red sphere. That's what I'm trying to figure out. I'm going to call that X. The distance between them is d1 squared. This is Coulomb's law. So basically, and times K. So I basically just apply Coulomb's law for the force of the red sphere on the blue sphere. Well, I know that's equal to the force of the y, I'm sorry, I just realized that's the x component. That's equal to the x component of the yellow sphere on the blue sphere, and that is q times 2q, again Coulomb's law. The distance between those two is d2, that quantity squared, times k. Okay, sorry, that's the magnitude of the total force, okay, not the x component. The x component, so force of yellow on blue x would be equal to force of yellow on blue times cosine theta. So, okay, so if red on blue, that's this guy right here, let me circle it, that is equal to this, and that is equal to this, and this is equal to that, then I'm going to do a lot of substitutions now, okay? Scoot that up a little bit. There we go. Okay, so I've got Q times X K over D1 squared. That's F red on blue, that's this. Okay, is equal to Q times 2Q over D2 squared times K. That's this, but it's times cosine X. Or cosine theta, sorry, not cosine X. I can cancel some things out. Cancel my K's out. Cancel one of my Q's out here. And I've got X over D1 squared equals 2Q over D2 squared times cosine of theta. I have to solve for X, that's the unknown charge on the red guy. Scoot this up a little bit. So X equals 2Q D1 over D2 squared times cosine theta. That's the charge on the red sphere, so that the net force on the blue sphere is perfectly negative in the y direction. I hope that helps. I know it was a little cumbersome, but that's how you use the force diagram for the blue sphere to be able to solve that along with Coulomb's law. Hope that helps.